We're going to look at the principle of relative motion and introduce some techniques used in interpreting a relative motion display. We can see 5 boats moving in true motion. That is to say, we are seeing their direction and speed against a fixed background. We're now going to focus on the boat following the grey track, travelling up the middle of the screen. Imagine we have a camera fixed directly above it, with the frame of that camera being shown as the outline of a radar display. As the other boats enter the area covered by the radar display, we see their motion relative to the grey boat. The green boat appears to be tracking slowly on a diagonal from the top right hand side of the screen to the middle of the left hand side. The red boat is steering 090 and is tracking diagonally down the screen. This is relative motion. If we remove the boats and replace them with radar targets, it is easy to see how newcomers to radar can get confused. The difference between true motion and relative can be dramatic. Relative motion is a result of the combination of the direction and distance travelled by the target and that travelled by the grey boat at the same time. Let's rewind and focus on how we use the relative option to our advantage. In the early days of radar, the only way to work out risk of collision or a vessel's heading or aspect was to use plotting sheets. And whilst the principles around plotting are the basis of relative motion, we are not expecting candidates to do formal plotting. All radars will be able to display relative motion with a trail of historical motion across the display. Most will allow you to set the trail to represent movement over a set period of time, 15 minutes in this example. The trail instantly gives us a relative track that we can project forward to assess which are the bigger risk. We need to know our own boat speed, 8 knots in this example, and the scale of the radar display to be able to interpret this to give an approximate aspect of the target vessels. First, we approximate the distance we have travelled in 15 minutes, 2 miles in this case. We then apply this to the origin of the trail. This will give us a reasonable estimate of each target's aspect using the same basic principle as formal plotting. This can be applied to all the targets. Having the aspect of each target is useful in terms of situational awareness, but unless we are able to see the vessels themselves, we should follow the guidance in Rule 19. This must be emphasised to students at all times. If the radar is stabilised, this trail could also be shown as a relative vector. Both trails and vectors can be set to true or relative if the radar is stabilised with heading, speed and GPS data. My personal preference is true trails, showing the true wake of the target, and relative vectors, meaning those pointing at me are the ones to prioritise. Sadly, the functionality of leisure sector radars varies greatly, and not all permit a split of true and relative trails and vectors on each target. However, most will enable a split screen mode. In this example, each section is referenced to head up, HU at the bottom of each section, with the left section showing true vectors, indicated by TV at the bottom, whilst the relative motion radar display on the right is showing relative vectors, RV, on the bottom. We don't know our boat speed or time frame for the vectors in this example, which would be something we would add if talking to students about this image.